Hi everyone, my name is Setareh and today I'm going to talk about time-lag multidimensional pattern connectivity, which is a novel metric for AG/MG applications. Why we need connectivity methods? Well, connectivity methods are essential in order to understand how different brain regions interact and how they function as a whole network. There are lots of methods out there, but only a few of them have exploited the multidimensional information. And that's why we think to get the most information out of brain networks, it is essential to look at multidimensional data and temporal information. But what I mean by multidimensional data, as many of you know, in any brain region like this, there are multiple vertices, each having a separate time course of brain activations. What univariate and conventional methods usually do is reducing all these vertices just to one vertex by averaging using PCA and other methods. This reduction, however, usually leads to loss of information and false findings, and that is something that we are not interested in. So that's why multidimensional approaches have been of great interest in recent years. The main motivation behind our method were two groups of studies, both aimed at looking and studying brain connectivity in terms of the multidimensional patterns of responses in regions. In the first study, they transformed the patterns of responses into another space using PCA. And then they took the first 1, 2, 3 principal components in order to characterize their final multidimensional space. But with this transformation, the genuine voxel to voxel relationship is being lost. And that is a limitation and issue that has been addressed in the second study. So what they do is they try to understand how well patterns of responses in one ROI like this one can predict another patterns in another ROI like this one through a linear transformation. So they keep every vertices and there is no transformation in terms of changing the voxel space. The point that I should add here is that most of multidimensional approaches have been introduced for fMRI applications. And here in this study, we introduced time-lagged multidimensional pattern connectivity, which is well suited for EG/MG applications and is suitable for event-related designs. And because it is EG and MG, it suffers from leakage, we did some subsampling for vertices using clustering as a pre-processing step. Essentially, we want to see how well patterns of ROI-X at time point Tx, like this one or this one, could predict patterns of ROI-Y at time point Ty through a linear transformation. So we are interested to see if there is a relationship between any pairs and how strong that relationship is. To quantify the connectivity metric, we used explained variance between the real output and the predicted one. The best score would be 1, suggesting a strong linear relationship between two patterns, and close to 0 or negative value suggests that there is no relationship between two patterns. Okay, before going any further and apply this method to a real data set, we decided to have a very simple simulations. Here, we computed the connectivity for univariate and multidimensional pattern connectivity. And to have an assessment of our method, we also varied critical parameters such as SNRs, number of trials, and number of vertices. We imagined 3 possible scenarios, the first one being 2 patterns which are completely uncorrelated and unrelated. So as you see, there is no mapping between patterns in X and Y regions. Another scenario would be when we have 2 patterns that are linearly and strongly connected through a coefficient matrix like this one, like T. And the point here is that all vertices or time courses are uncorrelated to each other. So that's why I call this one multidimensional effect. There can be something in between in which there is a relationship, but not all vertices and time courses are independent. So basically, they are showing the same activation, and that's why we've called this one univariate effect. So we compute the connectivity with univariate and multidimensional pattern connectivity, and here is the result for the first scenario in which we have two independent patterns. On the left, we see the result of univariate connectivity, and on the right, we see the result of multidimensional pattern connectivity. Both x-axis shows the number of trials, so we are having different number of trials, and y-axis shows the connectivity metric, which is x-plane variance. We also computed the connectivity for different number of vertices, so that's why we have different curves. So for both univariate and multidimensional pattern connectivity, we get close to zero values, suggesting that there is no connectivity when it comes to independent patterns. Here in the first row, we are actually looking at the result of the second scenario, in which we had patterns with univariate effect. For all panels, the reddish curves show the result of univariate connectivity, and the greenish ones show the result of multi-dimensional pattern connectivity. We have different number of trials, that's why we have different curves, and we have different number of vertices, that's why we have different panels. So what is important here is that for this kind of pattern, we get better results with the univariate connectivity, as you see, is performing better than the multivariate one. But this multivariate pattern connectivity is still sensitive to a great amount of data variance in all cases. For the last scenario, in which we had patterns with multidimensional effects, we see that this multidimensional, the univariate connectivity fails to capture more than 20% of data variance, whereas the multidimensional connectivity reaches 1 in ideal cases with high SNRs. So in total, the simulation suggests that multidimensional pattern connectivity is sensitive to both univariate and multidimensional effects and performs well in the case of independent patterns. Okay, as a next step, we apply this method to a real data set, to an existing data set, to compare the connectivity of semantic networks in two visual word recognition tasks, namely lexical decision and semantic decision task. In the semantic decision task, people needed to retrieve more specific and detailed semantic information. That's why we call that one more semantic. Whereas in the lexical decision task, people only needed some amount of semantic processing. That's why we call that one a less semantic one. In terms of the region of interest, we looked at left and right anterior temporal lobes as two critical regions for semantic representation, posterior temporal cortex and IFG as two important regions for semantic control, visual area as the input of this network, and angular gyrus because it's a controversial region in the semantic literature. Okay, this figure gives us an idea how and what connectivity looks like on a real data set for, in this case, for left ATL and IFG. So this is a connectivity between these two pairs at different latencies. So the first column shows the result of semantic decision. So color bars show X-plane variance, the connectivity. The second column shows the result of lexical decision connectivity. And the last one shows the comparison, the statistical comparison through t-test. And these bright colors show latencies that have been modulated by task demands. Well, I computed the connectivity between any pairs of regions with both univariate and multidimensional approaches and put the comparison in a bigger matrix, so this one. In upper diagonal, we see the result of univariate method, and lower diagonal, we see the result of multidimensional pattern connectivity. What is striking here is that with this new method, we are getting not only more pairs of regions that have been modulated by task demands, but also more latencies that have been modulated. So in this case, we see that all semantic regions, including left and right ATL, posterior temporal cortex, and IFG, have been modulated by task demands, whereas that is not the case with the univariate connectivity. So this one is more sensitive to changes. Okay, up to now, we were talking about linear multidimensional pattern connectivity, and all of us know that linear methods can be a very good approximation for nonlinear ones as well. But here we want to see whether or not nonlinear methods can improve and complement linear approaches. So instead of this linear transformation, what happens if we replace it with a neural network, which is a nonlinear function? Okay, we did the same procedure, but this time with neural network. And in terms of the simulations, we have the first one, independent patterns. We have the linear multidimensional effects as a second scenario. But for the nonlinear multidimensional effects, this is not as straightforward as other scenarios because there could be several choices for that nonlinear functions, for that nonlinear mapping. And what we chose here as the first step, just something to start with, was the model that has been suggested for neurons, for actually how neurons spot in the brain. We do not know anything about how patterns are being transformed in the brain, but we use that model. So to do so, first we transform the first space, the first pattern with a linear transformation, and then we apply sigmoid function as a nonlinear function here, and then the output of that nonlinear function has been transformed through another linear transformation to yield the final patterns of responses. Again, we varied critical parameters. We computed the connectivity for linear and nonlinear multidimensional pattern connectivity. For the first scenario, we see that for both linear and nonlinear multidimensional pattern connectivity, we are getting close to zero value, suggesting that there is no connectivity for independent patterns. So both of them are doing perfect. For the second scenario, in which we had linear multidimensional effects, we have a different level of SNRs again, different number of trials as different carriers, and then different number of vertices as different patterns, different panels. The greenish ones, the greenish carriers show the result of nonlinear multidimensional pattern connectivity, and reddish ones show the result of linear method. So what we see here is that the linear method is performing slightly better than the nonlinear one, but nonlinear one is doing really great. So both of them are really good here. For the last scenario, in which we have nonlinear multidimensional effects, we see that the nonlinear method is outperforming the linear one in all cases, except for the last one, in which we do not have enough number of trials. So when it comes to neural network, it is essential to have enough data to be able to produce a meaningful result. Okay. As before, we then applied the nonlinear method to the same data set. And here in the upper diagonal, we see the result of nonlinear one, and lower diagonal, we see the result of the linear one. So the most significant difference between these two methods is that we are getting two more pairs of regions that have been modulated by task demands, namely right ATL on large iris and right ATL PBA. And the other point is that you are getting more latencies that have been modulated by task demands. Take a look at these two examples, which are the connectivity between the same pairs. With this one, we are getting more lags or more latencies compared to this one. Okay, to summarize the result of all methods that have been implemented on the same data set, so lexical decision and semantic decision, I brought this figure. So in our very first study with coherence, we got the modulation between left and right ATL at early time points, and then between left ATL and IFG at later time points, only two connections. But with this multidimensional pattern connectivity, we are getting this kind of modulation. So we see that almost all of semantic regions are being connected to each other from the very early on. And it gets even more complete at later time points. And even with the nonlinear one, we are getting more connections, suggesting that this method can yield a more complete picture of the brain. Well, to summarize and conclude, time lag multidimensional pattern connectivity is a new bivariate functional connectivity metric. It investigates the multidimensional relationships between patterns of event-related brain activation in space and over time, and it is well suited for EEG-MG applications. We ran some simulations to compare the univariate and multidimensional pattern connectivity, and it revealed that our method is sensitive to both univariate and multidimensional effects and performs well in the case of independent patterns. We then compared the linear and nonlinear multidimensional pattern connectivity with simulations, and the results suggest that the nonlinear one is more sensitive to different effects, especially nonlinear ones. Semantic-wise, in the semantic network, we saw that our new method, multidimensional pattern connectivity, was able to identify task-dependent connectivity changes across the whole semantic network. And it showed richer connectivity compared to the univariate approach that we chose, and coherence. And as to the future direction, as this multidimensional pattern connectivity was a bivariate functional connectivity, we are thinking about taking one step forward and propose all-to-all multidimensional pattern connectivity, or a multivariate multidimensional pattern connectivity. And as the probably last step, we are thinking about benefiting from autoregressive models and propose effective multidimensional pattern connectivity. Well, that's it for me. Thank you so much for your attention. I'd be glad to take your questions.